I'm going to talk about coroutines like so many other people did. So there was a good chance that you know about coroutines already. So I just want to get the practical matters. So the reason I'm presenting that is pretty much all compilers, well, major compilers support coroutines. I've definitely used them with GCC, Clang, and Visual Studio. It works fine. There may be some quirks, I don't know. I haven't noticed actually anything which blocked me or something, so it seems to be okay. So people can actually use that in the wild. Sadly, C++20 has no coroutine classes. It has all the coroutine infrastructure, and you can do it, but it doesn't ship with anything making it nice, like let's say a generator. And we managed to get generator kind of relatively late in the game, finally into C++23. But we don't have anything else interesting. For example, there's no task. The reason we don't have a task is simple. We don't have an async abstraction yet. Now, async abstraction, having a task is kind of weirdish, but people may still want to use it. So let's talk about how you can use it without standard library support. And one thing which I found is nice with coroutines is they have an interesting interface which actually makes it possible that I use my task, you use your task, and they can still interoperate in a way so that I don't need to know mutually about one or the other, which is pretty cool. So despite everybody going off their rocks and doing something different, it kind of can come together. We probably don't want to have everybody doing something different, but we could, it's not a blocker. Okay. Why is co-await interesting? This is not the generator approach. It's basically more the idea of I have something which is not ready. I want to await it. The obvious example is I/O, right? You're reading from a keyboard, you're reading from the internet, from a socket, whatever you read from, even from a file. It's not there yet. You're waiting for that. You could block a thread. Blocking threads is bad. Switching context is relatively expensive. Maybe in the meantime, we just switch over to do a different jobby and the same thing. And if nothing is there, then we wait. Obviously, external interactions are kind of I/O as well. You could wait on unavailable resources, right? We have a limited set of file descriptors. Maybe you go, all right, I don't accept another connection until I have actually file descriptor available. There are some cool other ideas is, let's say you do a database access, and your database may or may not have an async interface. Most have an async interface as well. But even if they do, maybe you want to lower the number of requests and batch things up. But you don't want to have that batching logic all over your code. It's often easier to go, all right, I process one thing at a time. But it would be nice if these things could still be batched up secretly. You could use co-await to go co-await the database result and have that be taking care of the batching. Originally, I tried to do that in the presentation, but this is another presentation. I need 2 slots for that, I think. In general, kind of any kind, oh, yes, the last one, delayed access, is an interesting one. Gornishanov, who did coroutines, actually has a lovely presentation where he talks about nano coroutines, where he goes kind of, well, maybe we just advise that we're going to access memory soon, and carries on doing that for a number of things, and then comes back to actually accessing the memory. So the idea is to reduce the latency of the actual memory access from whatever it takes, like the 60 nanoseconds for it to get from main memory into the CPU to just the 4 nanoseconds you get to access data. So coroutines, as they are done, are apparent, and people apparently use that for good benefit. Coroutines are fairly cheap, so you can do these things, which is kind of cool as well. Okay, so the key things on coroutines, which I think is worth understanding, is that there's basically an awaiter, which is basically the abstraction of here's something we can await on, and we say, well, we interface that. I will show on the next slides how that looks like. And this is basically for specifying how work works, or how we specify asynchronous work. And then there's a promise type which specifies how the coroutine actually works. The promise type is kind of the key bit. There's a little bit of a coroutine class around, but we will see that as well. But these are the key things you basically write when you do interact with coroutines. So the more, well, important thing is kind of interesting. That's fine. The kind of central thing is how do I actually specify how work is happening. And this is basically the covate expression. This is kind of an operator. Covate gets an expression. It can return a value. It doesn't have to return a value. It can be void, like any function as well. And sort of what that expands to, this is a lie, what is on the slide. It's more complicated than that. But this is a good roadmap and is sufficient to understand what I'm going to talk about. Is if you call covate on the expression, it gives you an evator. And this evator is expected to have a member function called awaitReady, which says true or false, depending on whether this evator at this point in time thinks it has the data ready or not. If awaitReady says, I'm not ready, false, then it does a thing inside the block, which is basically await suspend. It calls await suspend, giving you a handle to a coroutine. A handle to a coroutine is basically something like a pointer to the interaction with a coroutine. It has some things on it. You can resume it, you can destroy it, you can ask whether it's done, can do a few things, but this is roughly it. And this is a coroutine which called the coawait, which already says something like coawait is something you can only call from within a coroutine. If you try to do it from elsewhere, there's no handle for the coroutine. And once await suspend returns, magic happens. This is the coroutine, well, is suspended. You can actually return values from there saying true or false, whether you really want to return or a coroutine handle to actually get resumed. I'll leave that out for here. Let's assume that doesn't do anything. So you can play a little bit different things, but if the thing suspend, then the compiler puts some code in to say, here's where I'm going to resume. And this happens when on this coroutine handle you present are given, whether it's through that channel or a different channel, doesn't matter. If the coroutine eventually gets resumed, the code carries on over there. That's basically the key coroutine magic. That's all it does. And when it resumes, it does what it would do if the code fell through, if the awaitReady had said true, and that is it calls awaiter await resume. And awaiter await resume does whatever it needs to do to produce a value, if there's a value, and if there's a value, it returns. Yes, Detlef.
I always thought the awaiter is the thing you co-await, not the result of
Well,
it.
so the question was, wait, the awaiter is the result of, is the expression over here, what you co-await. Actually, not quite, and we will see that in a bit. The expression over there, I would rather call is a co-awaitable. It's something you can co-await. What that actually means, and we will see that as well, depends a little bit on the coroutine it gets called from. But the important part is, out of the co-await operator thing, you get an awaiter entity on which these things are called. So this is really what is happening there. Right, there's a little bit of more detail in which I left out over here to say, all right, well, if this thing returned true or false, it can return true or false. There's another chance to not suspend, or it could return a coroutine, which is resumed instead, but this is it. You can actually imagine this is how the expression is expanded. At least it works as a mental model, even if that may be conceptually wrong. Okay? So, the net effect of all of that is the Veda Tab basically has three operations. awaitReady, telling them whether it's suspended, needed over here. Await suspend, which does, all right, I set up whatever I need to do so that I can resume eventually, and probably sets up that the work completes. maybe, and then await resume to produce a result. And like I said, await suspend needs a coroutine. So what is a coroutine thingy? Again, here's a little bit of code which is entire pseudocode. This is not really what is executed, but it's reasonably close, I think. That's probably a lie as well. This F thing over here, in this case I didn't put any parameters, it can get parameters, but this F thing is basically sort of a coroutine function. It really is sort of a factory for a coroutine object. And if you call one of these functions returning a coroutine thingy, and, this is important, your body contains at least one of the coroutine operators. It contains co-wait, co-yield, or co-return. Then the compiler goes kind of, cool, that must be a coroutine. I do not pretend this is a normal function call, I do something entirely different. And this is what it does. And the function we have specified over here in the curly braces does happen, but it does happen in the middle of the code somewhere. That's things happening before and things happening after. The thing which happens before, the first thing is, it creates something like, I called it frame over here, which is kind of a coroutine frame. The coroutine frame is conceptually allocated on a stack. There may be cases where it may be elided, so it's not guaranteed that that new happens. But the coroutine frame is basically sort of a stack frame for what is happening inside our function and used to capture any arguments this function would have. In this case, it doesn't have any, but it could have functions. And it captures whatever the compiler needs that it can resume eventually, like this kind of a suspension point, kind of going, all right, I'm here and I need to resume somehow from here. This is what goes into this frame. And there's an interesting aspect of that as well. This new is actually called using, calls actually operator new, as one would expect, and you can overload that operator new. Oops. Oh, this is awkward. Come on. Okay, I need to press more often on the computer, which is fine. Most of the time I'm not talking about slides, I hope. So this coroutine frame goes on to, basically contains everything needed for capturing the body of the function, the variables, and what the compiler needs to operate. And you can observe the operator new if you have parameters and you overload it. Next, once it has actually this frame, and over here assume this promise is not a member of the frame, you actually never see the member. This promise thing is kind of inside, there's a promise thingy. So this promise type we will have a look at in a bit. There's kind of a promise type which we can control. And basically this promise type needs to have an operation called getReturnObject. This is how the actual result we return from this function is produced. This is kind of a wrapper for the coroutine, how you interact with the coroutine. Often it contains a handle or something, whatever it needs to interact with the coroutine. So you can maybe start it or get results or out over that or destroy it eventually. And we will see all of these things as well. So it does that. Next thing is, it basically calls, imagine this core thing is kind of a function. It kind of invokes a function with a try-catch block around it. Because it does that kind of asynchronously, we cannot have exceptions escape. There's a try-catch block around these things. Inside this thing, the first thing it does is it calls initial suspend and co-waits that result. Co-wait, we have seen what it does ready and these things. Then it executes a body, which needs to have at least one co-await, co-yield, co-return inside, and it may suspend multiple times. If it falls off that body, it basically does a final suspend, or actually if it returns, that's a little bit of a lie over here, but it would go final suspend, which again is co-weighted. So again, the co-wait logic over here can suspend in all these cases. You can also not suspend. And then another thing it does is the try-catch block. If an exception is thrown, it calls unhandled exception. It doesn't pass any parameters because, hey, maybe you don't need one. You can get hold of the exception by basically using current exception if you're so inclined. And then whenever it pops out of this function, and like all of these suspension points may basically go and say, oh, we suspend, in which case it drops out of that function. It returns the result we have constructed before. So that's a mental model of what these coroutine functions actually do. They're kind of more like a factory of the coroutine thingy, and once you suspend, you actually get the actual result. Although it may, if none of these things really suspend, just run to the end. Okay, so I hope that is reasonably clear. So let's actually use it. Oh wait, there's one more slide. So basically, these are the minimum 4 functions you have to implement for a promise type. Initial suspend, final suspend, telling you how to suspend, unhandled exception, dealing with exceptions, and get return object to get something. And now I have demo. So pretty much for the rest of the presentation, I'm gonna live code into that thing. Going back to slide 15 or something is not a thing. If you have questions, please ask directly. And I may not notice if you put up a hand, just shout out. Because it's kind of, there's a big light coming on and kind of I see there are people in the back. And I see a hand over there right now.
Isn't there a fifth function you need to provide, either the yield 4 or was it already yield 5?
See,
You showed on the previous slide there are 4 functions on the promise type you need to provide.
yes. And
I was under the impression there was a fifth one, to either yield the value or to say there is nothing to use.
well, we can try it out. I don't know whether that's a Clang specific. Clang only needs these 4. If you have a core return, you need to have, well, in any cases, you may want to implement extra functions. If you have a core return, you may need to implement return void or return value. If you have a core yield, you may need to implement, I think, yield value. So there are additional functions you may have to as well, but I think this is a minimal set to basically get things going, and then everything else may hook into these things as well. So it's not meant to be complete, nor is the code I've shown you, the pseudocode, really complete and true. It's kind of giving an idea roughly of what it does under the hood. Right. Okay, so I hope you can read the code in some shape or form. I can make it a little bit bigger. I can also, but then we have only fewer space. If people, I was about to say, if people in the back need the code bigger, there's a trick. You come all the way to the front, and then we also have an easier time possibly to interact. Okay, the file is pretty much empty except for a little bit something just to show potentially whether we have a memory leak easily. A track variable, you can just stick that into a class and it would track construction, copy and move construction. So it's not particularly interesting. I don't want to talk about that. Otherwise, there's a hello world. If we compile that, I think it's compiled, and run it, then it says hello world. Okay, cool. And as one would imagine, I want to use co-wait. I already mentioned that if I do co-wait over here, the compiler will tell me kind of, yeah, no good. And this is actually something I consider quite interesting. The error messages popping out of all of that are actually quite good at guiding you what you need to do, as we will see. So over here, yeah, co-wait cannot be used in the main function. Cool. Whether that is actually a helpful comment or not is in the eye of the beholder, right? Because let's say we do create a function f and say void f, because it told us not in main. Okay, fine. Let's do it in f. We can do that. Now it goes kind of, okay, still an error, as one would expect as well to some extent. Well, this function cannot be a coroutine. It has no member promise type. Okay, well, So what it says over here, you see that it goes coroutine traits. All of these things I basically pretend as a promise type inside. If you want to get the real details, it goes via coroutine traits thingy, but look that up. It's more interesting to see how these things often work, and I never interacted with coroutine traits directly. But it basically says, well, void doesn't do that. Okay, fine. I want to implement a class, a task really, so let's pretend we have a task. And it already tells us a little bit more, like this must be the void, the only void around, that this function needs, or this type needs a promise type. Okay, fine. Whether you have the promise type defined inline or ahead doesn't really matter. You can, as long as there's a type def inside promise type, it's fine. Okay, compiler goes, more errors, right? As one would expect, because I said, well, look, we need to implement a couple of functions. Initial suspend. Okay, so initial suspend. Do we want to suspend initially? And what do we want to do on initial suspend? So we need to come up with an idea what it should do. And over here, I go with, you know what? My task, although the task really should be lazy, let's kick it off for now. So to have something which kicks it off directly, we can go, yeah, we don't suspend. And there's a helpful Veda class, which is fairly trivial to write, called suspend never. And all we do is we return that. Okay, cool. Okay, yeah, I mean, okay. I mean, fingers, brain, finger connection, morning. So far I'm doing well, I mean. So, okay, well, more errors. So it also talks about over here something like int. We will get rid of that in a bit. Or final suspend. Okay, final suspend. You know what? At final suspend for now, let's not suspend. We will change that because otherwise it's not particularly, well, it is useful, but it's not what we really want. So final suspend, fine. What does it tell us next? But you can see already, as long as you know what these things are meant to do, you can go, oh, right, yeah, I forgot that one. Let's do that one next. This time it says us is, oh, it's required to be non-throwing. Okay, final suspend. Okay, fine. So no accept. It's one of the cases where the system actually forces us to be, to say no accept. Great. What's coming next? Okay, now it tells us first about the inside. Let's ignore that for a moment and go and say, well, we need to return, get return object. Fine, can do that. Get return object. What do we want to return? Actually, you pretty much need to return the outer type over here, the task. So we do that, get return object. And at the moment, I have no need for that. I just go, I return that. It's fine. And the next thing it will tell us is unhandled exception. Right, kind of, it says a little bit weird, but anyway, it says promise are required to remember unhandled exception. So what do we do with unhandled exception? I don't know. Somebody yesterday claimed, I think Phil, that unhandled exception normally just terminates. Let's not do the normal, right? Let's do something different. Let's say we pretend we have an error and we just do current exception. Right? I don't want to be normal, it's just not a thing for me. So current exception gives us an exception pointer, so let's stick an exception pointer in here. We're not necessarily going to use it, but you can see that you can capture it, and now the promise type contains the error if there was an error. We may want to do, maybe whenever we interact with that thing, in a real implementation, maybe we want to check whether there's an error and deal with it, and depending on what time it will be, we may get to that. But you could do that. So now it gets to, okay, reference time in is not a structure union type. That turns out to be true. So co-await basically wants to have something it can turn into an awaitable. An easy way to do is what Detlef had suggested, saying, well, it really wants to get an awaiter. So maybe we just give it an Evator. Let's give it an Evator. That's easy enough. And let's call it value Evator. It's not particularly interesting Evator, but it's meant to produce a value. So let's say we give it an int value. I don't necessarily think you want, and well, we can do the same exercise and going kind of all right, yeah? Sorry, it's still 17, so we go and create a value Evator out of 17. Well, I lost the 17. Don't want to do that. More importantly, it also lost a little bit of brightness, but let me know if you cannot see anything, then I need to deal with that. Okay, so value Evator. Okay, now it goes and says, well, you know, this guy needs await ready. Okay, await ready. We have a value, awesome. So await ready, we know what that does. Await ready does return true. Cool. And then next thing it will go tell us, oh right, what about await suspend? Now await suspend is interesting, right? The compiler could really see over here, even if I could make it context, but the compiler still goes and say, no, 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 I really want to create an await suspend. I always tell you, it's ready. You will never suspend. Compiler goes kind of, yeah, stuff it. Give me an await suspend. So I have to do it, fine. Await suspend. It gets a handler. Not gonna type it, too lazy. Auto. Okay, cool. And now await resume. All right, await resume. Yeah, over here we need to do something, right? We want to return an int, await resume. And we just return value. Cool. And compiler happy. Cool. Now let's see whether it actually did something. So we print that guy. And oops. Yay. Compiles. And value prints 17. Okay, everybody happy? We have created a coroutine. We have actually co-weighted something. And we have spent a lot of time to create a really trivial function. That is not particularly interesting, but now we have the infrastructure in place. Now, the first thing which slightly upsets me is that there's still hello world. Let's get rid of that junk. But over here, co-wait, it needs an Evator, that's what I was told. Let's get rid of that Evator and do something different instead. Now, this does not compile. We already know that. It tells us, well, it's not a struct type. Now, I need to know about that. I put it somewhere else, put it in front of the task. And we can actually tell the task in our promise type, there's a way to tweak things. We can go, we get a value. Maybe we want to do something. I'm not necessarily saying that is a great idea, but if I want to await values and I said I want to co-await everything, I want to clearly co-await values, we can do that. The way to do that is there's a function called await transform. Now the compiler will never tell us about that. So far the compiler told us do that, do that, do that. Await transform you need to somehow know. So await transform, often it's a template. We can make a template. At the moment our value type is not. Well, let's change that. It's kind of silly, so we make it a template. And every time we get something, type name value, every time we get a value, and over here this is absolute slideware. I'm not going to move or any of the forwarders fancy stuff. In real world you would probably do that. Await transform, we can just return our value type of E. Now, I don't recall if I make that a template, whether this does deduction correctly. Worst case scenario, we need to write, well, I'll make it V over here as well. Worst case, we may need to type, specify the type. But, okay. Use of undeclared identifier. Oh, but it's not value type, right? Everybody types value type all the time, so nobody noticed that I type value type instead of value Evator. Okay. Okay, and now it goes, oh, no viable construction or deduction. These core people, fine. Okay, now it compiles and it runs. And sorry, this was not running, this was running. Okay, so we can co-evade 17. Still not a big deal, but important part is we can co-evade something. Cool. And we can, roughly speaking, co-evade arbitrary things. You can actually tweak your coroutine task to, all right, I can evade these things and I do whatever I need to do. This is, for me, somewhat important considering that I want to deal with sender receivers. Senders are not evaders. There's something different. They have enough operations to implement a sender as an evader, but they are not. So, but I can create a task which recognizes senders and goes, oh, this is a sender, I hook that up and I co-evade whatever sender does. Sender are these things, I guess lots of people went to the keynote yesterday where Bryce had a slide full of inclusive scan, very important algorithm. And you probably want to implement it like that if you know what you're doing. But if you want a simpler version, you actually want to create a coroutine and you just co-evade a bunch of other things and everything reads so much easier. And then you go kind of, yeah, if that ever becomes a performance problem, I do the crazy. But I would imagine that nobody actually wants to use sender receivers directly, except the people who really want to tweak the performance and do things. And real people, that would be me and I guess most of you, would actually use a coroutine to actually do these things. So senders are important, although everybody yesterday probably went kind of, yeah, I'm not going to do that. That is not changing my life in any shape or form. So yes, it does, but not via that interface. But evade transform is the magic ingredient we need for that. Okay, so yeah, let's do something different. And let's, instead of co-evading 17, go, I will not do I.O., but I will pretend I do I.O. What about that? I pretend I read some value, well, something. So async read, let's call it async read, whatever. Let's say we have an async read. And this is probably not really the interface, but when you do an async read, you'd probably do something like an select poll, epoll, kq, whatever, something, IOU ring, some kind of context where you actually schedule your thing. I'm not going to implement that, but we would probably have some kind of context. And let's say we keep it simple, we just read from a file descriptor and we get file descriptor 1. So maybe we implement async read and we mock up the stuff. So I don't have a context, reading short name, let's call it IO. Let's pretend we have a struct IO, doesn't need to do any members yet. And then we create another evader, we have seen that. So I will actually short circuit a little bit on that. That should be over here, right? Because, yeah, let's not do that. But async read, most likely it's not ready. So we say it's not ready. What that means is we almost certainly get into this evade suspend function to do something. My async read, I will make it really simple and go, I read a string. Because I want to concentrate on the coroutine stuff, not on the IO stuff. So IO stuff all just mocked up, made simple. All right, we're going to return something. Okay, we return a value. That's cool. So we put a string in here, which is a value. It's not populated yet. So if we actually do these things, oh, I needed to, I stuck an IO in here. We probably have the IO context waiting over here. So we do context. Okay, cool. So this should pretty much, no, it does not. Conversion from IO to string. Okay, yes. Yes. All right, so my async read, actually, I wanted to give it the work. So basically, to schedule work possibly, we need to remember context. And I said, okay, it's probably file descriptor, so I store these. I will put curlies over here and async read. I don't think we really need the curlies already, but I don't recall whether Clang actually does a round thingy. Function to return type in what? No way. Oh. No, further up, well, this means, oh, this one. Let's briefly get rid of that. Yeah. Well, but this is a value of 8. Oh, I see. Oh, so I actually failed earlier, but it would have worked. Okay, sorry. Didn't notice that. Fine. No, I understand what you're saying. Yes. So, but it would have worked if I typed that correctly. So it's cool. What I actually want to do at the moment is go. All right, let's do the I/O thingy over here, right? If we execute that, it will not print anything interesting. It will just print. It actually doesn't print anything at all because we don't print anything. Well, we would print something. We would print the value if async read completed, but it never completes. So we just drop off that thing, so nothing interesting happening over here. What we actually need to do is in our await suspend, we somehow need to set up that our I/O knows about the I/O we want to do and somehow completes. Okay, so let's do that. Let's create something, let's say, on our context, we create a submit function. And the submit function, by all means, takes in a function object. And this is not going to be efficient or something, but you can get rid of all the objects if you want to. This is not a trick. So we will basically go and say, all right, we need to capture our file descriptor so that we can do something with that. And let's say we get our string back, which actually read, whatever, line, or, and well, we also need to capture this so that we can go and say, all right, when we submit that, we say value equals line. Right? And this is not sufficient because once we have set the thing, we need to go and say, oh, actually, we want to continue with the coroutine we have given over here, right? This guy we get as parameters, a coroutine we have suspended. If we have actually read our input, then we want to carry on executing. So we go and say, well, we capture this, or we don't, actually we don't need the file descriptor here. We put that on the other thing. So we want to submit when we have a read on this file descriptor that we get our awaiter, this, and the coroutine we want to resume and just go h.resume. That should be mostly fine, except that I need to type resume correctly, and I don't have a submit function. Okay, this is a mocked up I/O, so I'm not gonna pretend I have a real I/O, so I do an unordered map of my file descriptor type, and let's do just a function which we can complete with a string. Outstanding. This is the outstanding guys, and submit. I'm also not going to do anything fancy with submit. It kind of gets a file descriptor and a function. And all we do over here is we do outstanding of file descriptor equals function. I think that should do the trick for these. No, it doesn't.
Line 76, you've got a closing angle.
Oh, yeah. Yes. Thanks. Oh man, I like that. We need more of that at work. So I pretend you're ChatGPT, but I cannot use them. at work. Value equals line.
Await suspend is const. It's trouble.
Say?
Await suspend is const qualified.
Oh, await suspend is const qualified. Thanks. Then this is not going to work particularly well, so let's not do that. Aha. And then somewhere is a semicolon missing in line 91. Yes. Okay. Okay, once we get over that, so nothing interesting is happening yet either, right? Still no output. Oh man, this is disappointing. But we could go and say, well, let's say our I/O actually has a way to complete I/O operations. And let's say we do void complete. We say the file descriptor is completing, and we have a string which is the value we get. And all we do over here is we see whether we have that, so that we don't immediately crash if we don't. Or so outstanding of find of, no, not value, file descriptor. If it is not equals outstanding dot end, and I must have mistyped something, maybe not. So if I actually have that, oh. So in theory, I could now go and say, all right, I got a completion, so I could do second of value, right? And so you basically call the thing, this would resume things. Actually, we can do that. Let's quickly do two things. Let's say we get a first value, we get a second value. So we read twice, and then we go over here and we do so better capture this guy, just basically giving us back a task. And then I do, well, context complete with, I think we waited over here on one, and this is our first line. Then we do cout back in main. And then we do the same with the second line. And if everything goes well, okay, we do kind of a little bit of the play around with these things, right? We see, okay, first, this is not good. I want to have a different strings, otherwise you pretend it's something different. But right, so our co-wait, the first guy, produced first line. Then we have our second line, which actually produced second, and then there's this back in main thingy, but this is because we jump back to main, print it back in main, and then we come back, and then we print the second line. Right, so we get both of these lines printed. There is something slightly dodgy though, and this is in our async read thingy over here. No, not in this one. In this one, we actually keep the outstanding thing in there. So we should really go and outstanding erase, because otherwise there's kind of, we haven't really removed the I/O. And if we do it like that, it would not work. Right, the reason, you can actually demo that, did confuse me yesterday, right? You see it prints the first line, and then it goes second back in main, so it's get back in main, but the second completion didn't have any effect. And the reason it didn't have any effect is, well, when we called the, where's it gone? This complete, we basically, this call over here resumed the coroutine, executed the result, and scheduled another thing into outstanding, and then we removed it. Right? So it's basically, we have submitted a new I/O and it came back. So we cannot really do that. We need to do a little bit more fancy. We need to have something like our completion function being captured. Then we erase it, and we only call it once we actually have put back things into a correct state, and we do our async stuff. And now we have our second line back, right? And this is this is super simple I/O context, which doesn't do any I/O, but you can see that does the asynchronous, and we can run multiple of these guys and complete them if we are so inclined. I hope that is a little bit more showing that coroutines kind of do the trick. And let's jump and do a little bit more fancy things. And that is what we do at the moment is we can await an awaiter, which is cool. We can await a value, but not at the same time. So let's do a little bit of that so that we can just await them at the same time. Because I would like to go and say over here in the middle of these, I want to see out, for whatever reason, I may have a function which is not yet, well, let's say I'm in the process of creating to-be-made async, and I want to call that. So it's at the moment still a value, but it basically at the moment doesn't return an awaiter, so we, in the migration phase, but we already claim it as async. So I actually want to just return a value. So my usual 17. And now this doesn't work because we have, well, it doesn't know how to turn 17 into a awaiter. We had that code I just commented out. The problem is if I comment it back in, the compiler goes kind of, yeah, the actual async thingy, it doesn't know how to deal with that, right? How do I don't know how to, it basically produces the, you may remember yesterday's lightning talk going kind of, all right, we print all these things. Here's another example of that. This error message is not particularly helpful. So we would kind of need an await transform which captures the awaiters. So how do I capture the awaiters? Well, we could, of course, just go and say, oh, well, if you have an awaiter, oops, A, and then we just return the awaiter, and that truly returns the awaiter. But obviously, these two templates are the same. Right? It doesn't know how to choose between them. But we know how to deal with that, right? We have concepts. Yes. Let's do a concept, right? We all love concepts. So we go over here. This requires is awaitable, or is awaiter of A. And the other one, so that we only have one or the other, and put parentheses around that, is not an awaiter. Okay. Now the only question becomes is, how do we implement is awaiter? So template, type name, T, concept is awaiter. Okay, let's start off with we pretend it is. Obviously, it's not going to work because it goes kind of unknown type name requires. Oh, well, require 75. Let's requires. Where it's going to go? Well, more importantly, I copy and paste it. So this is actually V. But once we get over that, it will say, oh, don't know, you need to actually say a little bit more. Right? Reference type int is not a struct or union. Now, how do we actually define this thing over here? Well, we can do maybe requires and say we have a T, and then we could try to co-await T, maybe. Right? So we would normally write requirements, but compiler unhappy. Going kind of, oh, sorry. This is requires. Right, go kind of, co-await cannot be used in an unevaluated context. But we want to really test that. So, what can we do? One thing we could do, of course, is we could go and say, well, let's do co-await, and we do basically just a lambda function in here, and we test that one. Right, something like that should work. But it goes kind of invalid operands and still hasn't understood that. So the problem is we need to turn this guy also into a coroutine. So let's say is a Veda test or something like that. And now we need an is a Veda test, struct is a Veda test. Okay, so we went through what it takes to, wrong thing, this one? No, this one. Writing a coroutine type, we basically need these 4 functions, no, not this one, to do it. So this guy needs to have the same name as that one. Okay. And I think if we go lucky, then this actually works. So here's a test to figure out whether something is an evator, which is kind of coolish as well. So now we can actually do evade. Over here we can see, all right, these are actually creating evaders. This guy was just returning an int. I don't know how to co-evade void. So I would like to co-evade void, but I haven't figured out that. Fine. All right. The next thing is, of course, if I put all of these things together, but now I have maybe something else, let's say I want to read more stuff, and this is actually a task I have, and this may suspend on its own. Maybe I also want to suspend a task, right? So maybe instead of this guy over here, we go, well, let's copy that, and we have a task, G, which also gets an I/O context, and this is where we actually encapsulate our operations to read that second thing. Now we want to really, let's go for now with co-evade. We want to co-evade the result of G, right? So we can basically use normal functional decomposition. Over here you see a little bit of something which is happening if you actually want to have co-evatable things and you want to co-evade things. There's a little bit of infection of you need to do everything in a coroutine. Right? This is slightly annoying. This is the coloring problem Lucian talked about. We have to color all of these things bad because they're not normal functions, they're coroutines. So they have a different color. So we want to do that. Now, if I try to do that, this is not going to work, right? Because our coroutine task does not, what? Okay. Well, this is not going to do what we wanted to do, at least, because, and I can show that, I was confused that it compiled, but our coroutine, or our task thingy is not an available, and it's not really a value, right? But we treat it as a value. And if we execute things again, it actually looks as if it works, but it doesn't. This is embarrassing a little bit, but okay. The reason it looks as if it works is, well, it starts off that task and immediately finishes because we have a suspend never in the beginning. But we really want to evade more things. Let's evade the third line. And then it doesn't work because, yes, we completed this one, we complete the third line. Third line. It now should have three lines completing. Okay, see, this is what happens if you do live coding, and also completes the third line. Okay, fine. The real problem which I had hoped to show, and I don't know why I showed that. Maybe it was because I actually do things eager. Maybe I need to turn it into non-eagerness. And so, because it at the moment just behaves like a function, it finishes, yes. So there's a little bit of a concern about these things, like if you get a coroutine, you normally don't want to really run to eager completion. So I think this is what I think Phil said that yesterday. So basically, typically you typically want to actually suspend over here always, which immediately has some interesting aspects, and we need to do a bunch of work to actually get rid of that. So, and if I run and actually don't kick things off eager, it only prints back in main. It never starts a coroutine, which makes sense. We never started the coroutine. So how could we start a coroutine? Well, the answer to that is we can give our coroutine some kind of function to actually do it. We could, for example, give it a start function. Let's put the start function over here. Ignore that guy at the moment. Let's rather start it. Okay? Now, start at the moment doesn't do anything yet. Now, how do we start a coroutine which is suspended? Well, we kind of know. We kind of somehow need to do something and resume the guy, right? So how do we resume it? At the moment, we can't, because our function doesn't know about that. But this is where this getReturn object comes in conveniently. So we could go and start off, what about if we return the promise type, okay? So we basically return a pointer to the promise. And this means we stick that into our task. Oh, let's do it after over here. Over here we have a promise type, pointer promise. And then we can do, well, promise. Promise doesn't really help us directly, right? So the thing is, the control of the coroutine stuff is all on a coroutine handle. But here we get a promise. Or I put in a promise. We could get a coroutine, but we can actually, if you have a promise, we can get a coroutine handle. This is kind of cool. So the way to do that is there's the coroutine handle type, coroutine handle of a promise type. So earlier you saw in the suspense thingy over here that I get a coroutine handle with no parameter. This guy can basically take either a promise type or void, and kind of coroutine handle of void behaves a little bit as if the coroutine of a promise converts to coroutine of void. So you can convert a coroutine of promise to a coroutine handle of void. So sometimes you need to know the type, sometimes you don't. Over here we probably eventually will need to know the type. And to recover the handle from a promise, you actually do need the type. So coroutine handle from promise type, we can go and say, oh, right, oh, cool, there's a from promise. Okay, and from promise actually takes a promise reference. Okay, we have a pointer to a promise, so we take a promise reference. Reference, and this gives us a handle. Well, we can give it a name, and then we can h dot resume the handle. Okay? Okay, not h equals resume or something what I typed, but this. Okay, now we are back into the first part of the function does work. So the first line and things we got back, but then we return into main and we don't do anything with a nested coroutine because we have not started it. So, and the reason we have not started is the coroutine we treat it as a value, we pretended it's ready, and that is all kind of not really the case. What we should do instead is go and say, well, our task, we probably want to have something like, let's say, a nested Veda to basically go, right, we have a coroutine, we run it, and we run another coroutine inside, well, or if you have a coroutine being called from a co-await, maybe we create a nested co-awaiter. and which is just the await logic as before. And we want to get that out. So when we call co-await, we want to get that one out. Okay, let's create a nested awaiter from an operator co-await. So this is if your class is not an awaitable and you don't want to rely on await transform, you can implement an operator co-await, although it unnecessarily it over here. Nested awaiter of whatever we need to give it. So you probably need to have some kind of context, and let's go and we give this guy just a promise type, promise to do things with. So we basically do this. And I think this is a great idea. Yes, thanks. I keep forgetting half the things when coding live. So I think we should see over here that we have a nested awaiter await ready call, just so that we can see that it's there. Bool const express never produces. Okay. Let's get rid of these const express over here. This one would be fine, but we don't want it. Promise, yes. So if we actually create this guy, we don't want to pass in this, but promise, yes. Okay, and I think we should now see when we co-await the thing that there's an, await red, but that we actually call into the thing, nothing happens because we don't do anything yet with the coroutine. So now becomes the interesting thing, what do we do over here? When we get a nested co-awaiter over here and we say await ready, actually we don't want to say await ready true, but we want to say it's false because we want to execute the nested one. We get over here essentially a continuation where we eventually, when we finish, want to carry on doing. But this guy gets suspended while we get activated, okay? So we want to do two things over here. One of them is we want to activate ourselves. That's pretty much what we did over here in the start. So this is the promise type is the coroutine we had, so we want to resume that. And we need to do something over here with the, continuous a keyword, continuation. We need to do something with the continuation. And, so the continuation is for the outer one. Okay, let's look at that, and I will put in a little bit code to show that it actually doesn't happen yet. But the continuation, we need to effectively store somewhere away with our promise so that when our promise knows we are done in our coroutine and there's a continuation, then we jump into that, sort of. So I will, for now, just stick this guy over here into the promise. So it's a coroutine handle of void. We don't know what type this actually is. So continuation. And let's set that up right away to be actually the no op coroutine handle. Oh God, no. I will get back to that. I need to remember what that name is. Because we actually not yet continuation. We're not yet using it other than remembering it for now. So this guy we had seen. So over here we go on the promise type. We have no continuation, and we say this is a continuation. Yes. So now we should start seeing, if everything compiles, that we do. Okay, we go into the nested one. Okay, now I'm confused. We resume this guy, and my personal hope was that it would now actually start executing the nested coroutine. Does anybody see why it doesn't? We say, okay, let's debug that quickly. And so we go and say, oh wait, did it just not? No, this is the output. So we say that the await ready is false, so it should actually come over here, right? So we should be in the nested await suspend. Suspend. Okay. This looks as if it has not. Oh, okay. Okay, this was somehow not, didn't execute things. Okay, cool. So there's an await suspend, then we are back in main, and we get the second line output from the function we had created over here. So this is cool. But what doesn't yet quite work is the bit over here. So cout, let's go fend or something like that to say we actually came back over here after we awaited this coroutine. And while we executed the nested coroutine, we have not resumed the outer one yet. We have a continuation, we know where to do it, so we actually need to resume it. Okay, how do we resume that guy? The answer is, we actually know that, okay, well, why is the error message so big? We know that when our task runs to final suspend, we are done with our task. Maybe this is a place to resume the outer one. Seems like a cool idea. Okay. Oh man, jumping around like no good. Final, over here. So how do we actually do that? Well, the answer is suspend always doesn't really do the trick for us, so we need to do something different. So we do basically a final evator to go and say, this is what we actually do over here. Say? Oh, yes. You're absolutely right. We need in the task. Thanks, I would have been really confused about that. Right, so we need the final evator in our, hopefully, task thingy. And the final evator should actually do pretty much what suspend always does. So let's do that. And because it always suspends, and the one thing we do different is we do await suspend differently. So we do an await suspend with some handle. What we really want to do over here is we want to go and say, well, we have a continuation, and we want to resume that. Right, this is basically just the guy outside. Now, instead of suspend never over here, we actually want to do final evator. And, oh, wait, continuation, we need actually know about our promise type. So promise, we need to have a promise type in here. Promise type, promise. And we need to return that. Okay. Oh, finale. And more, unused parameter age. Okay. So over here we get a handle. This is actually our own handle, sort of, for the coroutine in the final suspend. If we actually get that handle, there's nothing good we can do with that, other than possibly destroy it. And we don't want to destroy it quite yet. So we want to destroy it actually from somewhere else. I can will show that. But anyway, the important part is that we resume our continuation. And this is going to work a little bit. If we type everything correctly, use of non-static data member, tasks from promise type. Oh, this is not promise, this is this. Right, this is, we are in the promise type over here. The promise type. Yeah, too many E's, don't know. Fingers, time to wake up. Initialize of iris, no. Element requires braces. Ah, this is the base class. I always keep forgetting the base class. Oh, and now we have to make everything no except. Final suspend is required to be non-throwing. Well, we claim that it is, but this guy over here is not. No except. Okay. Come on, run. This is also not quite what I was hoping for, because now we actually call the continuation. There's a bug in there, but not this bug. Oh. No, this guy we should actually see f end. Shouldn't we? When we continue the... What did I do wrong now? I mean, there are a number of bugs at the moment, which I'm aware of, which should, however, not have the relevant effect. So one of the bugs we have at the moment is we actually have too many allocations compared to the instructions. We don't actually clean up our tasks. Maybe I just do that and maybe find the other bug which we have. To just quickly demo that this is actually the case, let's give this guy another member over here. So we have a couple of members already, and we do this funny track member, and we give it a name, task. Maybe actually make it a little bit stand out. And hopefully this works, and we run it. Then you can see that we don't construct anything. Oh, we need to execute that. Oh, okay. This is better. No, this is good. This is good. What had happened before, I saw still the output of the previous run. Because this guy actually does say fn, so we actually did jump back. We crash. Crash is good. I like crashes. The reason I like crashes is this gets me back into, I know what that problem is. Right? So, but there's another problem over here. You can actually see that we have multiple constructor calls, but there's no destructor call. So we have a memory leak. And we crash. Now, let's go for the crash first. The reason for the crash is actually quite simple. Over here, we always call continuation resume. But the outer coroutine, we actually never resumed, and we didn't get a coroutine handle. Okay, so it's not surprising that it crashes. So this is not a valid coroutine. What we could do, however, is we could, instead of expecting a valid coroutine, just go and say, you know what, we just initialize this guy over here with the no of coroutine. And I think this is all we need to do. Does that compile? Yes. And if we do that, then the crash is gone. So this is a good start. This would also mean that we could actually do something somewhat neater with all of these things. And the main thing is we could, instead of doing the await resume over here, we could actually go and return over here coroutine handle, and instead of resuming it, we return it. And this is better because the coroutine handle return from await resume, if you return a coroutine handle, actually gets resumed. But the await resume stack frame has been removed. Otherwise, you basically may end up multiple times calling that in a loop, and you basically have an infinite recursion and eventually crashes. Whereas if you return the coroutine handle to be executed, you take that stack frame off. There's an opportunity, and I think it's even guaranteed to do a kind of tail recursion elision, and it actually loops, and you don't have that overflow. So this is actually a really useful technique. I think it's called synchronous transfer. Okay? So a couple of few minutes more, and I want to spend them, instead of doing anything fancy, going kind of, well, we have a bloody memory leak over here. What to do about that? The answer to that is we could just go and say, in our task, we currently store a promise type. Let's not do that. Let's instead store something different. Let's store a unique pointer. Right? I like unique pointers, great. This of our promise type and of the promise. Well, this won't do the right thing, right? The way to delete a promise is not by delete. Would be obvious choice, but that's not what we need to do. We need to do something different over here. So you just pass it a deleter. And what we have to, and then we also need to do, I think somewhere, well, that's sort of as a deleter. So the deleter we want to have is basically a function which, given a promise, gets a handle and destroys the handle. It's a little bit around the block. But this is effectively all we need over here. So we do a lambda auto. I need to do something a little bit fancy because I need to know the promise type. So, well, we know the promise type. Let's maybe do that. Promise type, pointer promise, and then we just do the same thing we did, and this is an expression, so we actually need to get the type of the beast. And because we have no lambda capture, we can actually instantiate the thing based on the type. So it's kind of cool. And then we do something very similar to that guy. We get a handle from the promise, which is called P over here. And then we do destroy. The thing about this deleter and this unique pointer is I type them out over here, but you can, and I need to type destroy, but you can entirely, fine. You can entirely package that up as an, let's say, unique promise or something like that. You just go have a template unique promise of P and get rid of that. So if I execute that, of course nothing works. Type of stuff. Oh, yes. Over here it goes. I don't know what that is. Okay. So in get return object, I need to do something different. Ooh, this is annoying. Because this basically means I need to do, well, let's say, I do using unique promise equals that, so that I can just create it. Then I have a unique promise, and in my get return object, I actually need to construct one. Promise. Okay. Is that happier? Let's see. No viable conversion from return type unique promise to task. Oh. Yeah, this is just okay. I need to put the task around that as well, and then I should be fine. no viable conversion from promise type to... Oh no, it needs to do something different. This used to be a pointer, but it's now an nested evator. We need to not use a unique promise because we don't want to manage it. It's just a pointer, it's just a reference, which basically says wherever we do that, which happens here, over here we need to call get the pointer out of the unique guy. Okay, now we should be able to run the thing, and it actually does the task constructor. It does, well, you can see one constructor over here, one constructor over there, and then two destructors. We called all the things, and I basically await all the stuff. Okay, I have 8 minutes to go. Instead of trying to do something fancy, which would be the next step for me to do, and is entirely doable, it's just kind of possibly not in 8 minutes typing, being a little bit nervous by now, would be to actually be able to co-return values from a task. What you do over there is you basically put in an something like, return void if you have none, or return value if you have a value, and you basically just stick them away somewhere. You do things, because we had stored away our exception. If we access a value, we would probably look at the exception, throw it if we want it, and all these things. I will put that little bit of additional code into the code I will submit, but I think I'm not going to do that in the next 7 minutes. That would be too confusing for me or I'm too nervous for that by now. So I want to point at a couple of resources. One of them is I basically learned how to use coroutines between the compiler messages and Louis Baker's blog. I did mention the nano coroutine stuff, which I considered actually quite interesting by itself. And the code for this presentation, like the code I just typed in, will emerge in that repo, probably in with the name task.cpp for now. It may go probably task -accu.cpp, because I may present the same thing and use the same URL. And with that, I go, any questions?